Somewhere inside a lab in Pasadena, a group of scientists stared at a number on a screen and stopped breathing. Not because something had failed, because something had worked. A number that was supposed to be centuries away had just collapsed into a handful of months. Nobody outside that room knew it yet. No headline had been written. No government had issued a statement. But in that silence, the entire architecture protecting the modern world, every bank account, every encrypted message, every military secret, every dollar of Bitcoin ever mined, had quietly, invisibly started to expire. And the machine responsible for triggering it wasn't even a quantum computer. It was an artificial intelligence sitting inside a laptop, trying thousands of ideas a human would never have thought to try, and finding the one that changed everything. This is not a story about the future of technology. This is a story about right now. For years, we were told a very specific bedtime story. Quantum computers, the kind capable of breaking modern encryption, were always 10 years away. Not 5, not 2, always 10. It was a comforting number because it meant nobody alive today really had to worry about it. Governments could plan around it. Corporations could delay upgrading their security around it. Ordinary people could ignore it completely. But here's where it gets worse. That 10-year number wasn't based on some fixed law of physics. It was based on how fast humans, alone, without help, could solve an extraordinarily difficult set of engineering problems. And in early 2026, something entered the equation that humans had never had before at this scale. An artificial intelligence capable of testing thousands of scientific hypotheses in the time it takes a researcher to finish a cup of coffee. The 10-year countdown didn't slow down. It didn't even hold steady. It buckled. According to informed sources close to the research community, the shift began quietly, almost accidentally, inside a lab connected to Caltech. A researcher named Robert Huang, who had previously worked inside Google's own quantum division, was wrestling with a problem that had stumped physicists for years: how to make atomic quantum computers, machines that use single atoms as their fundamental building blocks, dramatically more efficient. The existing method required somewhere between 100 and 1,000 atoms just to encode a single functioning qubit, the basic unit of quantum information. That ratio made large-scale atomic quantum computers a distant fantasy. Too many atoms, too much noise, too much instability. Huang decided to try something unconventional. Instead of relying purely on human intuition, he fed the problem into an open-source AI optimization tool, one that harnessed large language models to search for better solutions, the way evolution searches for better organisms: trial, error, mutation, survival. He didn't expect much. In his own words, he didn't think the system would find anything useful. Read that again. One of the world's leading quantum researchers assumed the machine would fail. It didn't fail. It found something nobody had seen. The AI-optimized algorithm reduced the number of atoms required to encode a single qubit from the hundreds down to just 3. Not a marginal improvement, a 100-fold reduction in the physical resources needed to build a functioning atomic quantum computer. Huang and his colleagues spent months trying to break their own result, testing it, stress testing it, trying to find the flaw that would explain it away. They couldn't find one. What they found instead was confirmation that the machine had combined fragments of scientific knowledge from wildly different subfields in a way no individual human researcher had ever attempted, producing something genuinely novel. Not a shortcut, not a trick, a real verifiable leap. And this is where everything changes, because a more efficient atomic quantum computer isn't just a scientific curiosity. It is, quite literally, the architecture of the machine that could one day break the encryption protecting the global financial system. Think about what that means for a second. Every secure website you visit, every bank transfer, every piece of classified government communication, every cryptocurrency wallet holding billions of dollars in value, all of it is protected by mathematical problems that are, for classical computers, essentially unsolvable within a human lifetime, factoring extremely large numbers, solving elliptic curve equations across enormous key spaces. These problems aren't hard because nobody has thought about them. They're hard because the raw computational power required to brute force them would take longer than the age of the universe on a normal computer. That has been the quiet, unspoken assumption underpinning digital trust for the past 3 decades. Break that assumption, and you don't just break a website, you break the digital nervous system of modern civilization. This is not chaos. This is strategy. Except the strategist, in this case, wasn't a government. It was mathematics, accelerated by artificial intelligence, moving faster than anyone had budgeted for. Word of the breakthrough didn't stay contained to academic circles for long. What most people are not seeing is the sequence of events that followed, and the sequence matters more than the discovery itself. Before the research was even published, the team behind it, now operating under a startup called Oratomic, founded by scientists from Caltech, Berkeley, Harvard, Amazon, and Google, quietly briefed United States government officials. Not after the paper went public, before. According to people familiar with the process, the agencies typically consulted on research with implications this serious are the National Security Agency and the National Institute of Standards and Technology, the two bodies most responsible for America's cryptographic defenses. Think about the significance of that sequence. A private research team, moving faster than most national laboratories, discovered something powerful enough that the government needed to be looped in before the rest of the world found out. That is not how routine academic breakthroughs are handled. That is how discoveries with national security consequences are handled. But here's where it gets worse. Oratomic wasn't the only player racing toward this frontier. On the very same week, in a moment of timing too precise to be coincidental, Google's own quantum division published a parallel and equally alarming result. Their team, led by researchers including Craig Gidney, one of the most cited names in quantum resource estimation, announced they had dramatically improved the algorithm required to break elliptic curve cryptography, the exact mathematical system protecting the vast majority of secure internet traffic today, including cryptocurrency networks like Bitcoin and Ethereum. Google didn't release the algorithm itself. They released something almost more unsettling, a zero-knowledge proof, a cryptographic method of demonstrating that they possessed a working algorithm without revealing exactly how it worked. In plain terms, trust us, we have it, and we're not showing you. Two of the most capable quantum research groups on the planet arrived at devastating breakthroughs in cryptographic vulnerability within days of each other, independently, while quietly informing each other's networks along the way. Days before the announcement, Google had already posted a job listing seeking a quantum researcher specifically to develop what they called AI-based discovery pipelines, systems designed to let artificial intelligence hunt for scientific breakthroughs, the same way it had just hunted one down for Oratomic. And in an almost theatrical piece of timing, less than a week before both papers dropped, Google announced an entirely new internal atomic quantum computing initiative, a direct pivot toward the very technology Oratomic had just revolutionized. This is where the real story begins to surface, the one most casual observers missed entirely. This wasn't a single discovery, it was a convergence. Multiple labs, multiple companies, multiple governments, all racing toward the same terrifying finish line at nearly the same moment, each one aware that whoever gets there first doesn't just win a scientific prize. They gain the theoretical ability to read the encrypted secrets of everyone who hasn't yet prepared. The number that came out of these papers should stop you cold. According to the Oratomic resource estimate, a fault-tolerant quantum computer using roughly 10,000 reconfigurable atomic qubits could be sufficient to break the elliptic curve, cryptography protecting Bitcoin, using an optimized version of a mathematical method known as Shor's algorithm. 10,000 qubits. To put that number in perspective, earlier estimates published just months prior, in February of the same year, had placed the requirement at around 100,000 physical qubits, and that estimate itself was already 10 times lower than what Google's own lead researcher had projected only a year before that. Read that progression again slowly. 100,000, then 10,000, in the span of roughly a year. The timeline to a cryptographically relevant quantum computer isn't just shrinking, it's collapsing at an accelerating rate, and artificial intelligence is the accelerant. And here is the detail that should genuinely unsettle you. Caltech, one of the institutions behind this research, has already built a functioning atomic quantum computer array containing 6,000 qubits. 6,000, when the threshold identified for breaking one of the most widely used cryptographic standards on Earth, is estimated at 10,000. That is not a distant hypothetical anymore. That is a gap that could close within a handful of hardware generations, not decades. Think about what that means for the institutions that assumed they had time. Cloudflare, the company responsible for securing a significant fraction of global internet traffic, didn't wait to see how the story unfolded. Within days of these papers surfacing, Cloudflare's own cybersecurity researchers described the news as, in their words, a real shock. One serious enough that they announced they were accelerating their internal deadline to transition to post-quantum encryption, moving their target date up to 2029, not 2035. Not some comfortable distant milestone. 2029, 3 years from now. One of the most quantum-prepared organizations on the planet, a company that already routes the majority of its traffic through post-quantum encrypted channels, looked at this new research and decided their existing safety margin had suddenly become too thin. But here's where it gets worse. Global regulatory guidance, the kind of guidance governments and industries have been quietly relying on to plan their cryptographic transitions, has generally pointed toward a 2035 deadline for migrating vulnerable systems to post-quantum encryption. That guidance was built on the old assumption, the 10 years away assumption, the one that just got shattered by an AI system optimizing algorithms in a matter of weeks. If the frontier keeps moving at this pace, the institutions still operating on a 2035 timeline aren't just behind schedule. They may be planning for a threat that arrives years before they're ready for it. And this is where the story stops being about cryptography and starts being about power. Because whoever builds the first cryptographically relevant quantum computer doesn't just gain a scientific milestone, they gain something closer to a geopolitical weapon: the theoretical ability to decrypt communications, financial transactions, and stored data that were encrypted under the old assumption of mathematical impossibility. And critically, this isn't only a threat to data encrypted in the future. Security researchers have long warned about something called harvest now, decrypt later, the practice of adversarial states quietly collecting encrypted data today, data they cannot currently read, and simply storing it, waiting for the day quantum computing catches up. Every classified cable, every diplomatic communication, every piece of encrypted financial infrastructure that has been intercepted and archived over the past decade suddenly becomes a countdown clock. The question was never whether that data could eventually be read. The question was when, and that when just moved dramatically closer. What most people are not seeing is how quietly the balance of technological power can shift in moments like this. Nations don't announce when they're close to a breakthrough like this. They brief select agencies, they accelerate internal programs, and they let the public narrative remain comfortably vague. Quantum computing is still years away. While behind closed doors, resource allocation tells a very different story. The fact that United States national security agencies were briefed before the Atomic Papers publication is not a footnote. It is the entire story, hiding in plain sight. When intelligence and standards agencies want advanced notice of a scientific paper, it is because that paper has crossed the line from academic curiosity into strategic asset. And artificial intelligence sits directly at the center of why this line got crossed faster than anyone predicted. This is the part of the story that deserves far more attention than it has received. It wasn't a supercomputer that found the breakthrough algorithm. It wasn't a classified government project with unlimited funding. It was an open source AI optimization tool, one built on large language models, run by a research team that initially thought their own approach was failing. The system didn't just crunch numbers faster than a human. It combined obscure, disconnected pieces of prior scientific literature in ways that demonstrated something close to genuine cross-disciplinary insight, recognizing patterns buried across separate subfields of quantum physics that no single human researcher had connected before. The researchers themselves described the AI's output as understanding niche subdisciplines of quantum computing, testing thousands of variations in a process resembling natural selection until it converged on something that worked. This is not chaos. This is a new kind of scientific engine, and it doesn't sleep, and it doesn't get tired, and it doesn't need 30 years of specialized training to make a connection between two distant fields of physics. It simply searches relentlessly until it finds what works. And once you understand that, the real headline of this story reveals itself. It was never really about quantum computing alone. It was about what happens when artificial intelligence gets pointed at the hardest, highest stakes scientific problems in the world and starts solving them faster than the institutions built to manage the consequences can react. Quantum computing was simply the first domain where this collision became undeniable, publicly, with receipts, with named researchers, with government briefings, and with an industry-wide scramble to move deadlines forward by years within the same news cycle. Consider the layers of this unfolding slowly, because each one deepens the stakes of the one before it. First, an AI tool optimizes a quantum algorithm in a matter of weeks, achieving something researchers themselves didn't believe was possible. Second, that optimization reduces the physical hardware requirements for a dangerous quantum computer by a factor of 100. Third, a rival lab, one of the most resourced quantum research divisions on Earth, independently arrives at an equally dangerous cryptographic result within the same week, suggesting the frontier is being approached from multiple directions simultaneously, not just one. Fourth, government agencies are briefed before publication, indicating this crossed from academic interest into national security territory. Fifth, the entities responsible for protecting the world's digital infrastructure, companies like Cloudflare, publicly acknowledge they are moving their defensive timelines forward by years, essentially admitting the old safety margins are no longer trustworthy. And sixth, all of this happened not over the span of a decade, as the old comforting story promised, but within a matter of months. Layer these together, and a picture emerges that has almost nothing to do with technology for its own sake and everything to do with a race whose outcome could redraw the balance of digital power on this planet. Because in this race, the winner doesn't need to announce their victory. They simply need to quietly possess the capability while everyone else assumes they still have time. This is where the human element becomes impossible to ignore. One of the researchers behind the Atomic paper described this as the first piece of work in his career, where he personally felt the full weight of what they had built. Work with implications for society at large, work that represented, in his words, an entirely new regime. Not an incremental improvement, a regime change. And the co-founder of Oratomic offered a warning that deserves to be repeated exactly as it was given, without softening. The world, in his professional judgment, is not currently prepared. Not the encryption standards most companies still rely on. Not the government transition timelines still built around outdated assumptions. Not the general public, still operating under the belief that this entire category of risk belongs safely in the distant future. And here's the deeper unease sitting underneath all of this. This entire acceleration happened using an open source AI tool, harnessing publicly available large language models. Not a secret military supercomputer. Not a classified government lab with unlimited resources and total secrecy. A relatively accessible optimization tool applied by a small academic team produced a 100-fold efficiency leap in one of the most sensitive scientific domains on the planet. If that capability exists in the hands of a university research group operating in the open, publishing in journals, briefing government agencies out of a sense of responsibility, what does it mean for actors who have no intention of briefing anyone at all? What does it mean for state-level programs operating in total secrecy, with vastly greater resources, applying the same category of AI-driven scientific search to the exact same problem, without the ethical restraint that led this particular team to consult with the NSA before publishing? That is the question nobody wants to answer publicly, because the honest answer is unsettling. We don't know, and we may not know until it's already happened. Meanwhile, the broader quantum industry has been rapidly repositioning itself around exactly this convergence, almost as if the entire sector sensed the shift coming before the public did. Major hardware providers have spent the year pursuing what industry insiders now describe as a shift away from simple qubit count competitions and toward AI-integrated infrastructure, systems where artificial intelligence handles error correction, noise modeling, and calibration in real time, essentially acting as the nervous system that keeps fragile quantum hardware stable enough to be useful. Google's own Willow processor, the chip that first demonstrated error correction could scale rather than get worse as systems grew larger, was used earlier this year to achieve what the company called the first verifiable quantum advantage in history using an algorithm they named quantum echoes, a demonstration that a quantum machine could outperform classical supercomputers on a real, meaningful task, not just an artificially constructed benchmark designed to favor quantum hardware. Multiple hardware providers, from superconducting circuit approaches to trapped ion systems to neutral atom platforms like the one behind the Oratomic breakthrough, are now converging on the same conclusion from different angles. Artificial intelligence isn't a peripheral tool assisting quantum research anymore. It has become the primary engine driving the pace of the entire field. And this raises the question that should be sitting at the center of every boardroom, every national security briefing, and every conversation about digital infrastructure happening right now, whether people realize it or not. What happens to a world built on the assumption that certain secrets are mathematically safe once that assumption quietly stops being true? Because, make no mistake, nothing about this story has reached its conclusion. The researchers themselves, the ones closest to the technology, are explicit that significant engineering challenges remain before a fully dangerous, cryptographically relevant quantum computer becomes operational reality rather than a resource estimate on paper. Building 10,000 stable, error-corrected, reconfigurable atomic qubits and keeping them coherent long enough to run a complex algorithm reliably is still an extraordinary engineering feat, not a guaranteed near-term outcome. But here is the uncomfortable truth sitting underneath every reassurance. The distance between extraordinary engineering feat and achieved reality used to be measured in decades. It is now being measured, thanks to AI-accelerated research, in a currency nobody fully trusts anymore. Announced timelines that keep getting revised downward again and again, faster than institutions can adjust their defenses. So where does that leave us? It leaves major financial institutions and blockchain networks holding trillions of dollars in value secured by cryptographic systems that were engineered under assumptions now openly being questioned by the very researchers who study them for a living. It leaves governments quietly accelerating classified programs while publicly maintaining the comfortable fiction that there's still plenty of time. It leaves companies like Cloudflare moving their internal deadlines forward by years, essentially admitting in public that their prior sense of safety margin has evaporated. And it leaves ordinary people, the ones with bank accounts, digital identities, encrypted messages, and yes, cryptocurrency wallets, largely unaware that the mathematical locks protecting their digital lives may have an expiration date that arrived years earlier than anyone promised them. What happens next depends on a race that is now unfolding on multiple fronts simultaneously. Between labs trying to build the machine, between defenders trying to migrate systems before it exists, and between an artificial intelligence that keeps finding shortcuts nobody expected it to find. Nobody knows who crosses the finish line first. Nobody knows whether it will be announced with the same transparency Oratomic and Google chose, briefing agencies and publishing openly, or whether the next breakthrough happens quietly inside a program with no obligation to tell anyone at all. Nobody knows whether the next AI-discovered shortcut shaves the qubit requirement down by another order of magnitude, the way this one just did, collapsing an already shrinking timeline even further. What we do know is this: the comforting story that dangerous quantum computing was always safely 10 years away is dead. It died sometime in early 2026, quietly inside a lab, when a machine that wasn't supposed to find anything useful found something that changed the trajectory of global digital security. The people closest to this technology have already told us, plainly, without hedging, that the world is not prepared. The only question left is how many of us are willing to listen before the countdown finishes running out.